So this is a video for the second experiment in EET 1150. And again, I apologize that you don't have the equipment yet. I said I'm doing my best to get it to you as quickly as possible. As I said, even if you don't get the equipment for this course, we will be doing all the videos like this for measurements. You will receive the equipment because you will need it in future courses. So this is not equipment just for this course. This is equipment that you will use in future courses as well. You will be receiving this still even if you don't have it for this particular course. So let's go ahead and look at what we're going to be doing here for this particular experiment. So with this experiment, we're going to be looking at Kirchhoff's voltage and current law. Now, I'm going to just there's a little bit of background there, not a lot, but I'm going to go ahead and go here and look at the two circuits we're going to be building here. The figure 2.1 is the series circuit, and so there's two things we should be looking for, is that the current through each of these resistors should be the same. So we should get the same current. We'll compute the current, and we'll also measure the current coming out of the power supply. But we'll compute the current through each resistor, and they should be the same. Now, the voltages across each resistor will be different, but the voltage should all add up to 9 volts. And that's Kirchhoff's voltage law, that if you have a single loop like this, which is what we have a single loop, that since I have 9 volts here, there should be a total of 9 volts dropped across those 3 resistors. Now, the other circuit we're going to look at is a parallel circuit, where these things are all connected up in parallel. And if it's in parallel, this is where Kirchhoff's current law really comes into play. The voltages across each of those resistors should all be the same. So we should be measuring a voltage of 9 volts across each of those resistors. And then we can also say that the current, though, should be different through them. So we'll measure the current coming out of the power supply again, and look at the current by computing the current going through each of those resistors. And what should happen is if you sum up the current going through each of those resistors, it should be the same as the current coming out of the power supply, because that is what Kirchhoff's current law states. Actually, there's a typo there. It says to investigate the voltage law. It should be investigating the current law. I mean, the current law is the one that says the current going into a node equals the current leaving a node. All right, so those are the two things that we're going to investigate in this lab. And we're going to use the exact same equipment. Sorry about that. Hit my laptop and then suddenly everything went flying everywhere. We're going to be using the same equipment we did in the previous lab here. And we're going to use our breadboard, our power supply, and our multimeter. We're not going to need anything else for this lab. So what we have here is we have 3 resistors. Let me zoom in on these, or not zoom in, focus in on these resistors. We have a 4.7 k ohm, 1 k ohm, and a 2.2 k ohm. Now, I'm literally just using the exact same resistors that we did in the previous lab. So I am not going to measure the resistances because we already have done that. And if you want to see what those are, please refer to Lab 1 to get what the resistances are for these resistors, because I'm using the exact same resistors. There's no need to remeasure them. All right. Now, the one thing, though, that I have to do here is I have to change how my power supply is going to be functioning here. So I have my power supply here. Let me focus in on this a little bit better. And so I've got my 12 volt here and my 5 volt, and it's currently connected up to 5 volt. But I'm going to be using a variable one because it calls for 9 volts. Now, if you got, again, banana plug connectors, you could get a banana plug connector with alligator clips that you could easily plug into here. That would be nice. But I don't have that with me. And so what I'm going to use is I'm going to use the same wires that we did for the 5 volt. But then what I'm going to do here is when you open this, it's a screw thing, and there's a little hole that you can kind of insert that into, or or you can just screw it tight here. So now this is connected on the negative. Now I'm not going to yank on this really hard because you could still pull it out, but it's in there securely. And I'm going to do the same thing with the red one. If I can find where the hole is. There we go, there's the hole. And so I'm going to tighten this down as well. Again, I'm not going to yank on it, but now I've got that connected in. And so now I'm connected to my variable power supply. Now what I'm going to go ahead and do is I am going to take my DMM, and I am going to use the alligator clips that I have, that I showed you in the last video here. So let me show you what I've got here. So as I said, I have these here. I mean, over the years I've picked up all sorts of stuff that I've purchased and everything, but this is just a single cord. And as I said, you can buy these for like, they're honestly not cheap. They're like 15 to 17 bucks to get good ones. If you buy them just individually, like where you have a banana plug connector on one end and an alligator clip on the other, you can get them much cheaper. But for some reason, putting them in all in one cable, it jacks the price up. But what I'm going to do here is I'm going to go ahead and I want to measure this power supply. So I'm going to go ahead and connect it here and connect it up here. So I've just got the positive and connected. Now, of course, I want to make sure those aren't touching because I don't want to cause any kind of short. And I'm going to turn this to measuring DC voltage. I'm going to turn on my power supply. So it's currently measuring what was it currently measuring? It was currently measuring at 2.5 millivolts because that's set at, here I'm trying to have both things shown here. Hopefully my camera doesn't fall, my laptop doesn't fall all over the place. So here, why don't I set it down like this? So we've got 0 volts displayed here. Now the other thing on these power supplies, you want to make sure that there's this little current knob and there's this little dot here. You want to make sure that that dot is maybe a third, quarter of the way up, maybe even halfway. That basically tells you how much current you're going to let out. So right now, if I have it turned all the way to the left there, that means I'm not going to let any current out. So I could have a voltage, but there's not going to be any current. So it's kind of useless to have it like that. Now, if I turn it all the way to the right, that means I'm going to allow 3 amps to get coming out. Now, that doesn't mean you're going to have 3 amps, but it will have up to 3 amps. Now, we're not going to have circuits that require that much. So one way to kind of protect from things overheating or anything like that, you can say, well, I'm going to current limit myself, and I'm only going to put it maybe at a third of the way, 1 amp. I mean, that's still tons of current. We're probably not going to use even 1 amp ever, but that makes sure that I'll never run 3 amps through a circuit. But I do want to have some current running through it. Now I want to have this at 9 volts, so I'm going to go ahead and turn this dial here. And you can see you can turn it, and it gets a little fussy here, so you can see how sensitive it is. Now I went ahead and set it at 9 volts, and now it turns out that that reading is actually precisely what I'm reading here. Well, actually now it changed on me, of course. I have it set at 9 volts and it's reading at 8.99 volts. Now, this is never something you should try and say like, oh, I need to be exactly 9 volts. Because even if you're talking about a 9-volt battery, a 9-volt battery is the nominal voltage. That does not mean the voltage of the battery is actually 9 volts. And actually, over the life of the battery is going to start losing voltage. And so that 9 volt, like when it dies, it might be at 8.2 volts when it's dead. Not at 9 volts. And so, again, kind of if I just touch it just briefly, 8.8 volts. Like if you're setting your power supply and you could only get it to be 8.8, well, that's okay. Obviously, we want to try and get it to 9 volts because that's what we're simulating. So I'm going to, even though I just already had it so beautifully here, I'm going to fuss with it here and try and see if I can get it back to, there we go. 9 volts, or in this case, we'll take a measurement now because this is what we're going to use, 8.96 volts. So that is our power supply voltage, 8.96. All right, so I'm going to turn that off for now. turn off my ohm meter, and I'm going to disconnect it here. So I'm going to build my first circuit. Now I'm going to do the same thing I did before when building circuits, where I'm going to put in my positive on my positive rail here, if it will slide in here. Sometimes some of these holes don't like to take the wires, and I don't know why, but sometimes they fuss, so I just kind of move around because there's plenty of holes. And so I got my 9 volt and my ground in. And now it's time to build the 2 circuits. Now the one circuit is simply them connected in series. And let's go and look at that. That's the first circuit. So it's the 1K connected to the 2.2K connected to the 4.7. So I have a 1K here. That's connected. Notice I have it connected to the 2.2K. And then I have the 2.2K connected to the 4.7K. So let me this 4.7 lead is being annoying with me. Okay, so I've got those connected in here. Let me focus on that. Okay, so I've got my 1K connected to my 2.2K, which is then connected to my 4.7K. Now the other side of the 1K, of course, is connected into the 9 volt power supply. So I'll make that connection. And then the final connection I need to make is that this 4.7K is connected into ground. So I have it connected like that. So that's my series circuit. So I'm built at this point. So let me set up some measurement stuff here and refocus again. Got a glare coming in now from one of my lights, from one of my windows, I should say, not lights. Okay. So I'm going to be flipping the power here in a second, but we're going to be measuring the voltage across each resistor. Now I'm using these alligator clips this time as opposed to the probes like I did in the last video. These alligator clips, though, are wanting to turn my DMM all over the place. Okay, you can still kind of read the voltage there. I'll adjust it here, but what I'm going to do here is I'm going to put on this here. I'm going to attach to the red lead. I'm just picking out a yellow breadboard wire for no reason. I just grabbed a yellow one, and then I've grabbed a blue one here. So I'm attaching to these alligator clips a yellow wire and a blue wire. And then what I'm going to do here is I'm going to just go ahead and measure the voltages across each resistor. Now remember, you have to make sure that you have the high potential on the right side and the low potential on the correct side. So if I do across the 4.7K, we can see I've got it connected now where it's in those 2 little holes there. So instead of having to hold the probe steady, the alligator clips with the breadboard wires are all connected up. Now I'm reading 0 volts because I haven't turned my power supply on. So let me turn the power supply on. And so we're reading 5.33 volts across that resistor. So that would be our recording for that resistor. And so let me just move it to the next resistor. And we're measuring 2.498 volts across that resistor. That's the 2.2K ohm. And then the 1K ohm resistor is measuring 1.133 volts across it. Now, if we think about this, according to Ohm's law and everything else like that, and current, since the current's the same in there, and we know that voltage is equal to current times resistance, since this is a series circuit and the current should be the same through each resistor, we should be getting more current, more voltage across a larger resistor. Notice that the 4.7K ohm had the largest voltage drop, and the 1 kilo ohm had the smallest voltage drop. But now if I add all of those voltage drops up, I should be getting my 9 volts, or what was it, 8.92 or 8.96, I think is what it was. I don't remember. But what was in the earlier video. So if we add up all of those voltages, we should get 9 volts. Just like if you look in your simulation, if you have to do a simulation on this one, I'm not sure if you do, you would have the same result here, where if you add up the voltages on those nodes, you should get to 9 volts. And I'll show you what I mean by that in a second here. So that's actually all the measurements that we need for voltage. Now it says to measure the current out of the power supply. We're going to compute the current through all of the resistors, but I am going to go ahead and measure the current out of the power supply. So I'll go ahead and flip my power off for a second here. I'm going to break my power supply connection. Now this is what's also nice about the alligator clips, is I can say, okay, well, I'm going to put in the negative side of my DMM, the black cable, and then the red cable in on this. So now I have this nice connection. I want to make sure that I turn my voltmeter to measure milliamps to start with. And now I've broken the circuit so I can measure the current going through it now. And when I measure the current here, I am measuring 1.14, 1.15 milliamps. Now that's not too surprising to me, because the voltage across the 1 kilo ohm resistor was like 1.14, 1.15 volts. And well, if you do that divided by 1 kilo ohm, that gets you current. And so we should be getting a current. Now if you do, that's where you need to compute the current for each of these resistors now, based off the voltage measurements we did. And you should compare that to this measured current value, because they should be about the same. Now they might not be exactly the same, and that would be, reason is error in measurement device. Notice how it's even right here. We can see, and when I say error, maybe error is not the right thing, accuracy of the measurement tool. Because notice that it keeps flipping from like 1.14 to 1.15, kind of flipping back and forth. And I mean, I'm not touching the circuit at all. It's all connected up. It should be giving me a constant reading. And well, that either is a function of the power supply not giving me a constant voltage, or the current measurement device not being accurate enough. And so we have all of those little variations that could cause some kind of issues in the circuit. All right, but that's all the measurements we need for this circuit, so we'll be ready to build the next one. So the next circuit we're going to build here is in figure 2.2 here. And again, when you get your kits, even though we will have done these experiments and you will have been able to record the values and do some computations, I encourage you on your own time to kind of redo these, play around with the kit, because that's how you're going to learn how to get this, so to really get used to using these pieces of equipment and performing measurements. Let's go back to here, though, this parallel circuit, and now we're using all the same resistors. So again, I don't have to remeasure the resistances of those, but they're now in a parallel configuration. So I'm going to go ahead and find my camera thing here and go ahead and rewire the circuit. So first I'm going to make sure I turn off my power supply. I'm also going to make sure to turn this back to measuring DC voltage, because that's what I'm going to do first. And then what I'm going to do, it's going to seem a little silly to do this, but I'm going to stack my resistors here, because they're all connected together, but I'm going to stack them like this on purpose here, and you'll see why in a second. Okay, so I'm stacking them like here, like this. Now, in reality, what I could have done is I could have literally put them all in the same row, or in the same, like I could have done them like this, you know, where I stack them. I put one like this and then another one like this, because they're in parallel. So the tops and the bottoms are connected. But I'm going to do this because we're going to be measuring the voltages across each of the resistors, and it's going to seem a little redundant, but it's going to be driving home the concept that if things are in parallel, they have the same voltage drop across them. So this bottom side is connected to ground, this top side is connected to power. So now what I'm going to do here is just connect all of these up. So this is connected to ground, like this one is right here. So, and then I'm going to grab a couple more wires out of my breadboard box here. So I'm going to grab another black wire here. Okay, that's not black wire. So I'm going to draw another black wire here because this is ground, and so I'm connecting it up like that. And then I've been using orange for my power, so I'm going to connect them up like this. Now, as I said, it's not necessary to connect this circuit up like this, but I'm doing this just for measurement purposes, to make the measurements a little bit easier to take and a little bit more clear on how to take the measurements. And then I'm going to do compare like this. Okay, so we got this in parallel. Now we've got the circuit wired up. I don't have to check the voltage supply, again, because I don't have to check it because I haven't changed anything. Let me refocus on the ohm meter. Well, DMM. I call it an ohm meter. It's actually a digital multimeter. So I'm going to turn the power supply on here. And now I'm supposed to measure the voltages across each of those resistors. And so that's what I'm going to go ahead and do. But now because the resistors are kind of separated out like that, it's going to be easier for me to do that measurement. So I'm going to plug these wires in just like so. And we're measuring 8.93 volts across that 1 kilo ohm resistor. So that's the 1 kilo ohm resistor. Now I'm going to move this to the .7 kilo ohm resistor, and we are measuring 8.93 volts again. And so I'm going to move this now to the 1 kilo ohm resistor, and when I do the 1 kilo ohm resistor, I'm getting 8.93 volts again. Now, if we're used to the idea of things in parallel having the same voltage, we shouldn't be surprised by that. Now the last thing it's asking us to do is measure the current coming out of the power supply here. Now this is where, again, you're going to compute the current through each of the resistors, but I want to measure the current coming out of the power supply. So I'm going to turn my power supply off, and I'm going to pull this wire out. And just like we did before, I'm going to put it right there. I'm going to change this to milliamps, and I'm going to put the wires in here in series so I can measure the current. So now I'm going to turn the power supply back on, and we can see that I am measuring 14.98 milliamps of current coming out of it. Actually, it's going up to 14.99, so maybe it's 14.99 milliamps. Now it's up to 15. So we will, and honestly, some of this, believe it or not, the reason it's slowly changing is because resistance changes with temperature. And I'm just checking my resistors here. They're not hot to touch, any of them. But they are, there's definitely the 1 kilo ohm is warming up a little bit, and now I've had my finger on it, which is cooling it back down. So it's kind of funny here, but we'll go ahead and take 14.99 or 15 milliamps. Let's go ahead and do 15 milliamps just for a nice easy round number here. 15 milliamps of current that is coming into this circuit. Now if I scroll here to this here, I can see that this right here is telling me what current is coming out. It says it's 0.01, which would be 0.01 amps, which it's more than 0.01 amps. It's 0.015 amps. And again, the current is going up slightly. It's not going to increase forever. It's going to fluctuate and steady out at some point. And that again is because of the heat. And it's as I said, it's interesting. You put your finger on the 1 kilo ohm resistor, and that's what I'm doing right now. You can just see I'm putting my finger on the 1 kilo ohm resistor, and then my finger's cooling it back down because resistance does change with temperature, which is something we typically don't worry about because the change is so insignificant. Because at this point we're talking about a 0.01 milliamp change. So the other thing, as I said, you'll have to do is you'll have to compute the current through each of those things here. So now that we have that, let's go ahead and look at what we'll have to do in our report here. So let's go back to module 1 and let's go back to the template here for what we need to report. So the measurements, basically you need to make the you don't have to do a simulation here, but you need to add all of the appropriate tables. So you should have a table, basically like Lab 1 here, where you have a table of your measured voltage supply, the measured resistor values, and I know we didn't measure the resistor values here, but you should have that from the previous lab. Then, you could have a table where you have the resistors values. You could have one table where you have, for instance, the resistor value, the measured voltage, the computed current, things of that nature. And then again, what you should be able to do is talk about whether Kirchhoff's current law or voltage law is satisfied. So for the first one, we said the voltages across the resistors for that first circuit. And let's go look at that first circuit again here. For this first circuit, nope, that's the wrong one here. This first circuit, figure 2.1, if you add the voltages that we measured across R1, R2, and R3, we should get that 9 volts that we measured, or it was 8.96 or 8.92 or something like that. And then we're using that same voltage source for part 3 here, or for step 3 here, and we have this parallel, and we measure the voltage across all those resistors. So then you're going to need to compute the current. And now the current that we measured coming out, which was 15, it's actually stabilized as a side note to 15.02 milliamps. So you could always use that one. It's been that now for a couple minutes. 15.02 milliamps. Coming out of that there, the current going through those resistors, these 3 resistors, R4, R5, and R6, when you compute these currents, you should note that those currents add up to 15.02 milliamps. Now, it might not be exact, and remember, why wouldn't it be exact? Well, we have errors in our measurements as far as accuracy in our measurement tools, and that's going to incorporate a lot of error. And there are things, small things, that probably don't affect any of our answers, but they could, like we're ignoring all of the resistances of the wires. But they should be roughly the same. For instance, if we say that there's 15 milliamps coming out of the power supply, and we say that once we summed up the currents, we get 14.9 milliamps, okay, we're good. That 0.1 milliamp is somewhere, and that somewhere could be lost in accuracy of the measurement tools. So that is what you have to do for this report. Again, if you have any questions on what's required, please email me with your questions. We can also set up a Blackboard Collaborate time that we can talk through any questions you might have.